So guys, next thing we're going to look at is final thing in thermochemistry. After we've looked at all the different heats of reactions, if you like, the different types of heats of reactions, we're going to look specifically at what is known as Hess's law. Just to begin, basically Hess's law is a play, if you like, or an interpretation or a different way of saying the law of conservation of energy. And we've talked about this many times. Energy cannot be, and you study this for junior cert as well, energy cannot be created or destroyed, but it can only be changed from one form to another. So essentially that's essentially what Hess's law is based on. And what Hess's law states effectively is that if a reaction occurs, so what we're talking about here is, let's say, the formation of CO2, carbon dioxide. To make CO2, you have a route where you can add O2, so that if you burn carbon in the presence of excess oxygen, you can get CO2. So that's what we try to do in combustion to prevent the formation of carbon monoxide. But in any case, if we look at just this top direction here, you see, the amount of heat, now you look at that, that's minus. Is that given out or taken in? Of course it is given out. And you know that from burning anyway. So the heat loss going from reactant to product is minus 394. Now that reaction does occur when you do it in excess oxygen. Now there is another way you can form carbon dioxide from carbon. And that's if you burn it in deprived oxygen, essentially. You can make carbon monoxide down here. Now, let's say we don't know what that heat is. What heat is given out. We may assume it's given out as a combustion reaction. But we do know that to go from carbon monoxide to carbon dioxide here, a different reaction if you like, this now is the reactant, the carbon monoxide is the reactant. If you add oxygen to that, you get carbon dioxide. And there you have it, you see? Delta H3 is equal to minus 283. So that's the amount of heat going from carbon given out, because again it's minus, going from carbon monoxide to carbon dioxide. So it's an exothermic reaction as well. Now if we didn't know what this value is, we can calculate it. The reason we can calculate it is that it doesn't matter the route that a reaction takes going from reactant to product. Whether it's this top one, straight from carbon and oxygen to give you carbon dioxide, or if it's this route here that goes through an intermediate carbon monoxide, the same amount of heat will be given out. So if that's the case, you already have minus 283 given out. You could, like, what would you need to do to that, add or subtract to that, to get minus 394? Because you know both routes will be the same, you say. And of course if you subtract, you can do that in your calculator, but if you subtract another 111, that will give you, so those two figures, you know, I get a highlighter, these two figures, you say, that 111 and that right there, the minus 283, the two of those added together will be equal to this route here. So it doesn't matter if you go around through an intermediate to a product, or you go straight through, as you have here. You have a one-step reaction essentially, and this is a two-step reaction. The bottom one is a two-step reaction, top one is just one step. It does not matter. The amount of heat given out or taken in for a reaction will remain the same, irrespective of the route taken. And that is Hess's law. So the same amount of energy going from carbon to carbon dioxide will be given out, irrespective if you do it in a one-step reaction like the top here, or a two-step reaction like this bottom. And that's what Hess's law is in essence. It effectively means that the heat change of a reaction depends only on the initial and the final states of the reaction, and it does not matter about the route taken. So we only care about the initial and the final heats, and that's what we study. That's what Hess's law essentially is. You see, that's the sort of law of conservation of energy coming in there, that it cannot be created or destroyed. So when you go from one to another, like if there's intermediates along the way, heat might be taken in and given out, but that doesn't matter to the initial and the final. So this is another example of it. You say, going from reactants to products, doesn't matter if you go straight through A or you go through some sort of intermediate. Now you can think of an intermediate, of course there is the principle of an intermediate championship. So it's not, if you like, the bottom championship, and it's not the top championship. It's in between. And it's the same thing here. An intermediate is not maybe the initial reactant that you start with or the final product you end up with. It's a compound or a substance formed in the middle, and that's what's known as the intermediate. The energy change is independent of the pathway taken. This is a nice diagram. Some reactions have loads of different routes. Lots of reactions have loads of different routes. So it doesn't matter what route you take. You see, all that matters is to this value here, this delta H, the heat of a reaction. It's the initial value here and the final value down here, you see. Doesn't even matter if you go down below and you come back up. So it's just the initial, and you know that how to read a graph, of course. You know, you'll be reading the value of the y-axis there to give you the energy of the reactants here and the products here. And it's the difference between the two of those that is delta H. So delta H, if you like, for the overall reaction, going from reactants to products, depends only on the initial and the final, not the route taken. And that's essentially what we study in Hess's law. That'd be a nice law to come up, you know, if you understand it. You know, the definition should pretty much roll off your tongue. Doesn't have to be exactly word for word what I have there, but like Hess's law is by principle is very straightforward. And you think about it, it really only matters the initial and the final. And then for a reaction described by a given equation, the heat of a reaction equals the sum of heats of formation of the product. That sounds very, very complicated. Essentially, there it is, that less means minus. Essentially, if you want the heat of a reaction, and that symbol there, you know, from maths, the enalpathies or heats of formation of the products multiplied by their coefficient, you be careful there, minus the heats of formation of the reactants. And that will give you delta H. That will give you this value here. And that's all Hess's law is. Nothing more complicated than that. And this is what we can use to do the calculation essentially. But like, to me this makes a lot more sense when you're studying it as well, because you know you have the subtraction there. And if you look at this, you know, you're talking about going from, for this, this is actually, if you look at it, heat is, if your reactants have more energy than the products. So heat is given out. And when you think about that, that means that this would be an exothermic reaction, so there's a drop. So essentially you're subtracting, from the heats of formation of the products, you're subtracting the heats of formation of the reactants. And you know, that to me makes a lot of more sense than maybe there's other ways you can do it. Now the only thing you need to be careful with here, and it's really, really important to remember, that when you're calculating the heats of formation of the products and the heats of formation of the reactants, you need to make sure that you multiply them by their coefficient. I'll show you it in a calculation in any case. See, there's delta H. And if you look at it here, this is a nice diagram I have here to describe that. There's the heats of formation of the products. There's the heats of formation of the reactants. If we subtract this away from this, if you like, you will be left with the delta H. And it doesn't matter about the activation energy, because we only care about the initial and the final, not the route taken. And I hope that makes sense to you. That's a nice diagram to demonstrate that. Now I know normally we would have that the other way around, but if you like, you could think of this as after the reaction. Normally we'd have the products. It's the same difference, it's still the subtraction between the two. Normally we would have reactants written here, so it's not the easiest way of thinking of that. So you could flip that around, it'd be the same calculation. Maybe I should have flipped it around. So that's what it is. Now just remember to multiply by in each of the cases, but I'll show you in a calculation anyway, to multiply by the coefficient. The heats of the formation of the don't forget that one, that's very important. I just said that one. The heats of formation of any element on its own, essentially. Now whether that's like Ne, neon, or O2, O2 is still on its own. That's always 0. The balanced equation is for 2 moles. You need to be careful if you're calculating the heats of or the heat of combustion. You'll notice that if it's per 2 mole of the substance you're thinking about, remember those heats are all to do with per 1 mole. So if it's per 2 moles, you're going to have to divide it by 2. So just be careful with that. That's important. So you won't be given values for something like O2. So you must assume that that's 0. And then I'd like to go through this example. But what I'll do is I'll go through this example in another video, because I'll have to rearrange the recorder.